Certain problems of sequence. Okay, today two problems. Today one more problems. Show that the sequence Sn such that Hn will be 1 upon 3 plus 1, 1 upon 3 square plus 1, and so on, 1 upon 3 raised to power n plus 1. Okay, 3 raised to power 1 plus 1, 2 plus 1, 3 plus 1. Okay, this is monotonic or monotonic and bounded both. That means convergent. Okay, so it's like sequence. The sequence Sn such that Hn end up of the sequence is like. So I want Sn plus 1 term, Sn plus 1 in place of n plus 1, one more term, one extra terms. This n term, now n plus 1 term. So in place of n plus 1. Now subtraction. Okay, first of all, okay, monotonic xn plus 1 minus xn subtraction, positive or negative. So this one, this, what you see? Okay, this term cancel, all term cancel except last term 1 upon 3 raised to power n plus 1 is positive. Yes, for all the natural numbers. Okay, positive 3 raised to power n plus 1. Okay, positive values. So this is positive. So Sn plus 1 minus Sn is positive. Greater than 0. Or that means Sn plus 1 is greater than Sn. Is what? Increasing. Okay. Sn plus 1. Next term it will be greater than first one. Okay. Therefore, this sequence, okay, will be monotonic, increasing. One of them increasing or decreasing. Okay. Not both possible. It will be one of them. Okay. So the first point clear. Now second point is bounded. Okay. Bounded. So of course, as this sequence Sn is this like 1 upon 3 plus 1, 1 upon 3 square plus 1, and so on, 1 upon 3 raised to power n plus 1 is positive sequence. Positive terms are yes. So this will be Sn will be greater than 0. I want now less than some term. Lie between two values. Bounded means it is lie between two values. So greater than 0, less than some term is bounded. Both sides, lower bound and as well as upper bound. Bounded. Now we have about these terms. Relations are. So we have 1 upon 3 plus 1 will be less than 1 by 3. Yes. 1 by 3 square plus 1 will be less than 3 square, 1 by 3 square. Yes. Okay. Or in this way, 1 by 3 raised to power n plus 1 will be less than 3 raised to power n. Okay. So therefore, this your Sen is 1 upon 3 plus 1, 1 upon 3 square plus 1, and so on. 3 raised to power n plus 1 less than bigger values. So in place of this 1 by 3, in place of this 1 by 3 square, and so on, 1 by 3 raised to power n. Okay, Sn will be less than this. What is this? It's a geometrical series. Okay, geometrical progression or geometrical series. Okay. So this is geometrical progression with first term is 1 by 3 and common ratio So common ratio is this upon this, this upon this 1 by 3. Okay, then what is sum? Okay, therefore this will be sum formula. Sum will be what formula? A into 1 minus r raised to power n divided by 1 minus r. That is a general formula for sum of geometrical progression. So A, first term of the series, 1 by 3, 1 minus r, common ratio, also 1 by 3, and 1 minus r raised to power n, 1 by 3 raised to power n. Okay, so this completely calculation. So what is this? So this 1 by 3 and 1 minus 1 by 3, 2 by 3. Okay, and this one 1 minus 1 upon 3 raised to power n. So 3 cancel 1 by 2. So 1 by 2, 1 minus 3 raised to power n. Now this is less than. Okay, so 1 minus 1 by 3 raised to power n will be less than 1. This will be less than 1. 1 minus fraction less than 1. So Sn will be less than 1 by 2. And already we know it is greater than 0. So lie between 0 and 1 by 2 is what? Bounded. So therefore sequence Sn is also bounded. Okay, so moderately accretive and bounded. So last topic of this chapter, sequence chapter, will be Cauchy sequence. Okay, chapter number sequence chapter. So in sequence now, okay, is a Cauchy sequence. We find limit of sequence, so many theorems. Okay. Now what is a Cauchy sequence now? Okay. Definition. A sequence Sn is said to be Cauchy sequence if condition. So for every epsilon greater than 0, there exists a positive integer m, okay, such a way that for m and n, two numbers, both must be greater than this your m, then we have mod of Sm minus Sn is less than epsilon. Okay, you know limit of sequence. The limit of sequence is a L limit of the sequence L. So it is no L. So only Cauchy means two numbers are there, m and n, two numbers. Both numbers must be greater than m. That fixed value, positive integer m. And for conditions are Sm minus Sn, m and n, two numbers are. So Sm minus Sn must be less than epsilon. Okay, then such sequence is called as a Cauchy sequence. So So this is simple technique. Theorems are on this. Two theorems are on this Cauchy sequence. First theorem. Prove that every convergent sequence of a real numbers, okay, especially is a Cauchy sequence. Okay, every convergent sequence is a Cauchy sequence. Okay, convergent sequence must be a Cauchy sequence. So convergence, these topics. Convergence means limit exists. Convergence means what? Limit exists. Any limit here, suppose. So proof. So take one sequence. So standard symbol, let Sn be a convergent sequence of real number, and converges to, suppose here, converges to, suppose here some number. Always here limit of sequence, same symbol. So Sn be a convergent sequence of real number and converges to n. At least this Sn is converges to n. Symbol means what? This means what? Limit of Sn will be n as n tends to infinity. Convergence means limit exists. And now by definition of limit, okay, here is a limit. Therefore, by definition of limit, we know, okay, what? For every epsilon by 2 greater than 0, okay, there exists a positive integer n, suppose, then, okay, what we have. So for n greater than n greater than n, then we have mod of Sn minus L must be less than epsilon. I take epsilon by 2 times, epsilon by 2 and epsilon by 2 will be epsilon result. So first then epsilon by 2. So for n greater than n, then we have Sn minus L less than epsilon. Okay. So for so many n greater than n, so this is not only one n here. Okay. So many n's are. So therefore this is also similarly for m greater than m. This condition also true for every number n after the capital M. So there are so many numbers after capital M. So M is a suppose number. So for this is also true. So Sn minus L is also less than epsilon by 2. Okay, true for all the n. So all the m after m. Okay, so thus both the numbers m and n both are greater than m. I want in a sequence. Now show this sequence is a Cauchy sequence. So what is Cauchy? Just we define Cauchy. Sm minus Sn less than epsilon. So consider Sm minus Sn. Consider and finally show less than epsilon. So we have to use 1 and 2. So I want Sm minus L. I want Sn minus L. So I want L here. So Sm minus L adding and subtracting L. Okay. So Sm minus L, one factor, L minus Sn. I want Sn minus L, so minus n common. Okay, then Sn minus L also. Now mod, separate mod of Sn minus L, minus become plus, mod of Sn minus L. Okay. So Sn minus L less than epsilon by 2. This less than epsilon by 2 means epsilon. So thus, or m and n both number greater than n, then we have mod of Sn minus Sn will be less than epsilon. That is the definition of Cauchy sequence. Okay. Therefore, this sequence Sn is a Cauchy sequence. Okay. So every convergent sequence will be a Cauchy sequence. Okay. Real number especially. Second theorem, say on this Cauchy. Prove that every Cauchy sequence of a real number is bounded. Okay, so it is bounded. Okay, definition. Again, take one sequence. Let sequence Sn be a Cauchy sequence of real numbers. Cauchy sequence of real numbers. So therefore, just by definition, Cauchy by definition. So for every epsilon greater than 0, there exists a positive integer and then we have what? For m and n, two numbers greater than this m, then we have mod of Sn minus Sn is less than epsilon. Okay? General definition of Cauchy sequence. Now here in theorem, in particular, I take epsilon as a 1, and this m as a capital M. M and n greater than m or equal to m also. I take equal to chance. So epsilon as a 1 and m as a capital M. Then what we have? Okay, what we have? Mod of S capital M minus Sn is less than 1. Okay, so in place of m, capital M. In place of epsilon. Okay. Now come to bounded. Let me show bounded. So we have to show this sequence Sn is bounded. So when bounded, if you show mod of Sn is less than some number, okay, k suppose mod of Sn is less than some number, okay, k. Okay, so consider. You have to show mod of Sn is less than k. So consider mod of Sn. So we know, okay, Sm minus Sn, okay. So adjustment. So adding, subtracting Sm and adding Sm, adding and subtracting. So this as a one term, Sm as a second term. So mod of plus less than mod of first term and mod of second term. What you know? Okay, Sm minus Sm or Sm minus Sm, no problem. Same is less than 1. So is less than 1 and mod of Sm. So mod of Sm is less than this line 1 plus Sm. Okay, and we know M conditions M and N both are greater than M. Okay, so now I want some K. So choose some time. It's like, so choose K as a maximum of, okay. So I want a maximum. So maximum of all the terms mod of S1 after Sm after M, but before M, okay, we need. So all the terms are okay. So maximum of S1, S2 up to what? Sm minus 1. Okay, before M. After M, this condition true. Okay, so therefore up to Sm minus 1 and using this also, with this also 1 plus mod of Sm. Maximum all these terms. Okay, S1, S2, S3. Okay, Sm minus 1 up to M. This condition true after M minus 1. Okay, M. After M minus 1 and this term including. So is it some K. Okay, choose the value of K. Then what you say? So this your Sm is less than this K, because K is a maximum all these values including this. Therefore Sm will be less than K for all the natural numbers. Therefore by division are bounded, in that case this sequence Sm is a bounded. So it's like both the theorems, first theorem, second theorem.